Hello, mic check, check. Hello, mic check, check. கேக்குதா? Check. Mic check, check.
Remember the baby who came to me? Yeah. Iena. People hear this as Jena, Vienna. It's very difficult to explain. No. Yeah, call size. So the Americans landed the before, just to take away everyone, including Brown. What's the guy? The space guy. Yeah. So they're all in Jena. Yeah. So. Is it on?
You say
hello. I don't. Hello, is it on? Is it on now?
Yeah, because they are recording.
Okay.
Yeah.
Okay, sure. Got it.
Okay. So let us start. So good afternoon, everyone. So today it is my pleasure to introduce our friend A. Gopakumar, known as Gopu, or the head of Team Eccentric. So I think most of we know him, including NPTA members and non-NPTA members. So he works on gravitational waves, at least every aspect of gravitational waves. So I go to NPTA. So today he will tell us about multi-messenger gravitational wave astronomy with his favorite blazar OJ287. So please start.
Thank you, Manjari. It's always a pleasure to be here, especially, I'm kind of slightly nervous to kind of give this presentation in front of some of my heroes in general relativity. I don't work on GR these days, so I'm pretty safe. Yes. Okay. So today I'm going to talk about something I have been doing with a collaborator of mine from Northern Europe, actually Finland, for the last 15 years or so. So we are essentially looking for persistent gravitational waves. These days we are familiar with transient gravitational waves, so that's the distinction. And since I'm looking for persistent gravitational wave, I have some transient affiliations. I'm a researcher at TIFR. I'm of course part of NPTA, and then thanks to Balchandra, we are also part of IPTA. And I'm also an associate of a place called Center for Gravitational Wave Universe in Seoul in Korea. So this will be a rough plan. So I will be talking about this idea of persistent multi-messenger gravitational wave astronomy. These days, fundings are there only for multi-messenger astronomy, hence that pitch. And this can be only possible most likely during something called square kilometer array era. So that's what I will. And the reason why we are sort of excited about this is the possibility that there is a blazar, and I will tell you what blazar is all about, very brief. And we think that that guy is actually hiding a supermassive black hole binary. And I will give you the specification. And the reason for is that we have the habit of predicting certain behavior from this optically, visible object. And it turned out that this has lots of implication for something called Event Horizon Telescope, which some of you may be familiar, photo of the black hole, that's this guy. And then of course, one of my favorite consortium, INPTA/International Pulsar Timing Array. These are done essentially in collaboration with very young people and very young at heart people, Maury Walton and Loki Abhimanyu and some of these colleagues from, whom I have actually never met. So, okay. So we are all familiar with gravitational waves these days. This is the era of transient gravitational waves in the sense that the gravitational wave come and go. That's it. You don't get them back. Once it's done, it's gone. Okay, and we actually have such transient gravitational wave signals, roughly 100 of them. It depends whom you are going to ask. So this, and what are we seeing? We are essentially seeing, this is solar masses at the scale, and this is essentially, where we actually found roughly in the consortium. So what you have is that you get, these blues are all black hole. You find collision of black holes, which lasts essentially milliseconds. And then you find a bigger black hole. You detect that there's a bigger black hole. There are no observational signatures so far, but you detect. And you also see something called true neutron stars. So the yellows are for neutron star, and you get maybe a black hole, maybe a neutron star, we don't know. So this is what, and it's a very adventurous area simply because this was the dark sector of the universe which opened up. So you have no idea what it's going to bring you. But more exciting was this object. This is called 170817. This was an event where two neutron stars coalesced, and we saw gravitational waves lasting essentially more than 50 seconds. Remember, the first event was 200 milliseconds, and then these were, maybe 300, maybe a minute for the time being. But this guy lasted for something of the order of, again, ask whom depends on who you are, but it's definitely clear signal was there for 50 seconds. Not just that, look at this 50 seconds. So it actually increased from a frequency. This is called a time frequency map. In something like 10 seconds, it changed the frequency from 50 to something like 300 hertz. Okay, whatever signal. This is a chirp signal. So what they did was they figured out in certain part of the LIGO data, there is some signal. So essentially they did just a FFT in a small time interval, look at the power and plot that power. That's it. But that area was detected, of the data was detected using some simple templates, analytic templates. Anyway, we'll come into that. And 2 seconds later, they saw after gravitational wave was kind of detected, a gamma ray burst was seen. Very weak gamma ray burst. And within 11 hours, they identified a possible galaxy where an extra bit that you can see there, it came. And this is amazing. So you have a gravitational wave source. It's no more a dark guy. It has an electromagnetic counterpart, a possible electromagnetic counterpart in that. And then actually in optical wavelength, new object arose in that galaxy, not very far. It's actually 40 megaparsec. It's our, cosmic neighborhood. And this happened, and something like 10 days later, they actually saw it in Chandra X-ray telescope, and then a couple of weeks later in radio. And this opened up all sorts of possibilities. The paper came up with 50 publication. It's all got published in 50 paper bundle, and that's important implication not just for gravitational wave astronomy but for physics, astrophysics, cosmology. That it's going to take time, but I just want to give you a flavor. So if you have 10 such events, you should be able to measure Hubble constant in a totally independent way. It actually demonstrated that the gravitational waves and electromagnetic waves propagate, essentially as expected in, electromagnetic and general relativity and various other things. And it actually showed that two neutron stars collide to form short hard gamma ray bursts. Along with that, something called kilonova will appear. So the gamma ray burst, you need to get things pointed towards you. But kilonova, you don't. I mean, this was not pointing towards you. So you have to know where you have to look for. That we don't know. So most likely there was a black hole, but there is no observational signature of that. In third generation era, we should be able to say by looking at the quasi-normal modes of the so-called black hole. That will take time. It's not going to happen maybe in 30 years' time.
But there is no quasi-normal mode for the...
No, you don't detect those. Even in the first event, there is a signature. We don't really detect and say that I have several modes and I can see how they decay and then get the mass. No, that's not. We predict from numerical simulation. We said, oh yeah, most likely a black hole.
What is the mass of the object after the...
So the way to do that is to actually use numerical relativity to estimate.
Yeah.
And then since you know the initial masses, you said the numerical relativity says that the final guy should be so much, so much. So that's what we make the claim. It's not, it's an estimate, it's not a measurement. So that's, okay. Okay, so, but we would like to do persistent gravitational wave and electromagnetic observation with sources not in our stellar neighborhood, galactic neighborhood, but cosmological sources. And that should be possible thanks to this consortium called IPTA, where what we do is that we look for a bunch of millisecond pulsars. These are we essentially make one arm interferometer with the Earth and the pulsar. Pulsar is a cosmic clock. According to Einstein, it doesn't matter delta L over L, it's the same as delta T over T. You very accurately measure delta L over L, you measure gravitational wave. If you measure accurately delta T over T, you also measure gravitational wave. And that's the game. And it turned out that I will kind of show. So that's a consortium for many observatories. So this is the American one, Nanograv. You heard from Mora. And then you have the Europeans. And then you have the Indian Pulsar Timing Array, kind of thanks to Balchandra. That's headed by GMRT. And you have the Parkes Pulsar Observatory of the Australian using the venerated Parkes telescope. And the game is to detect nanohertz gravitational waves. So why am I kind of throwing words like that? That's nothing surprising here. We are all dealing with black hole binaries or compact binaries. These are self-gravitating system. They follow omega square r cube is GM. It doesn't matter. That's roughly good approximation. You can rewrite that omega square r cube GM, assuming that R and M are related, into this expression. So gravitational wave is related to the mass of the black hole. You can see that if you put 30 solar mass there, you are going to get 300 hertz, and that's precisely what LIGO saw. If you put a billion solar mass, you get a nanohertz gravitational wave here. Put a million, you like in our galactic center, you get millihertz, and that's what Lisa will eventually see. So that's the game. This is the characteristic strain, delta L over R. It's the same as delta T over T. And why are we excited about it? Because there is a hint that the pulsar timing array are actually seeing a diffuse but persistent gravitational wave background due to coalescing massive black hole binaries in our universe. There's a hint. These papers are, this is actually from Nanograv during the COVID. This was followed by the Parkes and then this is actually from the EPTA consortium. They're all talking about a possible signal which can be associated with gravitational waves from a ensemble of massive black hole binaries. Okay, why is that? Well, we are not going to see, like the transient signal for the time being. Why is that? Well, the question is it can be argued very easily. So what you do is that you actually ask the question, suppose I am observing using an interferometry, so an observatory of myself for gravitational waves. I take data for T observation. So then I have the frequency sensitivity 1 over that. Now you ask that this delta F sort of can be written in terms of dF by dt, and then can be converted into dN by dt and all that. So I ask the question, what will be the number delta n? I can rewrite this as delta n over delta t times delta t. Again, play around with the frequency. When I rewrite that, you actually can be written this in terms of dN over dt. That is the number of binaries merging per year. And some mass ratio, I kind of put it as 10 raised to 9. I say gravitational waves I'm interested is roughly nanohertz, and observe for 10 years. Then I find the number of such black hole binaries in an observational window T observe, hence the delta F, it will be around 3 times 10 raised to 12. And why this mass ratio comes is this thing comes minus F5 by 3 is essentially dF by dt, which we actually saw in LIGO. That curve goes up, frequency going up as a function of time is precisely that. So you can see that I can say this dN by dt is maybe not 10, maybe 1 in 10 raised to minus 6. It's still going to be sufficient number of black holes in a small frequency window, which is 1 over T observed. So in whatever you do, there will be a background. Whether it's strong enough or not is another question, but that's what people are trying to do. Okay, but this kind of pulsar timing array is one way of looking for gravitational waves. It's not just the stochastic gravitational wave that we are going to see. We will also see continuous gravitational wave. This is so-called timing residuals. So what that essentially means that LIGO look for delta L over L. How does they do? They actually look for photons coming out of the interferometer in a way. They actually operate it in a dark port, which means no light will come out of the interferometer. If gravitational wave passes by, they see residual light, which fluctuates exactly like the way gravitational wave kind of changes. So similarly, we have a good clock, and the clock will kind of move away from our expected behavior in a certain way, and we call that as a timing residuals. It's a slightly technical. I'm not going to talk about. Mora talked about it quite a bit. So that is the timing residual. If I can make pulsars as fantastic clocks to the accuracy of tens of nanoseconds, and that's a huge challenge, but it's possible. And then if I can observe, I will see gravitational wave like that. This is called the red, because power is more on the low frequency, and this is continuous, it's persistent. And then something called bus with memory. I'm not going to talk about that. So this can be also extracted from the data. Only thing is that it's not a small data set. You have to wait for it, do it carefully, and that's precisely what this consortium is doing. Okay, and what am I saying? So these are a picture of that, two black holes kind of going away each other, emitting gravitational waves, and that passing gravitational wave will actually disturb. Okay, now it's not working. It will disturb the Earth. It will also disturb the pulsar, and we find the signature of both in the imperfect nature of the clock we are trying to model. And that's the timing residuals I was talking about. So that's the game. But if such sources are there, it's of definite interest, not just for us, because all these sources are big black holes are reside in galaxies, and galaxies usually emit electromagnetic waves. So if there are two black holes going around, it will create electromagnetic waves by default. Therefore, this kind of systems are interesting to not just IPTA, it's also interesting to collaborations like EHD or its next avatar called NGEHT. So what kind of system am I talking about? I'm looking for a system like this. So we have seen galaxy mergers in beautiful Hubble pictures. So that's something like this. We actually have seen what will happen after two galaxies merge. The core gets merged here. Again, we have pictorial evidence of that from observation. We actually have radio signature of two black holes, but they are not very close. They're further away. And what we are looking for, two black holes which are at orbital distances, something like 10 raised to 4 AU. That's very close. It's called milliparsec, 10 raised to 4, 10 raised to 5. So AU is the distance between Earth and Moon. So essentially, things, two black holes in the roughly the size of the solar system are slightly bigger. And they emit gravitational waves, which PTS can see. And that's the game here. Okay. Eventually, they will merge and do many other things, but that's not the point. But why are we excited here? We have a tentative evidence that there is a black hole binary out there. It's actually emitting nanohertz gravitational waves. And we would like to confirm that, scenario with all sorts of observation. And this talk is about that. Okay. That's for the motivation. Okay. So what am I talking about? I'm talking about, this is a cartoon created by Abhimanyu and Robert in JPL. So this is a scenario we are talking about. I'm going to play this movie. You can see that there is a black hole going around that, hitting that whatever disk around that big black hole. And you can see that keep happening. Right? Have you seen that?
That's a supermassive black hole.
It's a supermassive black hole. And even the companion is a supermassive black hole. The reason is that what we do is that we think we are observing such a phenomenon from a active galactic nuclei. Okay. And these flashes are very powerful. They're actually, as powerful as 10 trillion suns. Well, there are two reasons. One is not that massive as the other one. Okay.
Supermassive.
It is also supermassive in our model, but that will take time. I'm not going to tell you what's going on right now. So what we do is that using post-Newtonian calculation, predict the occurrence of those flares.
So this is like a black galaxy merger.
It is essentially a remnant of a galaxy merger. So that flare, you can see that they are irregular. Okay. So that's essentially the take-home message. We try to predict them, make fool of ourselves technically, and if they come, it adds a piece of evidence to the possible model for this system. I will not claim that it is indeed a supermassive black hole binary. That's kind of foolish thing to do. Yes, Prabhu. Yes. Yeah. I'm sorry? Yes. It has possible a disk around it, but there's no observational evidence. There is few, but they are not very sure about it. If it has a reasonable disk, it actually can emit in sub-millimeter waves. And that's a hope for the EHT, and I'll come into that in a minute. So,
What about the orientation? So, and the orientation beside
which one? The disk. Well, it's definitely a possibility because the guy actually, the jet is actually pointing towards us. So this guy is huge, and it's a radio jet coming out of it. It's actually directly onto us. Therefore, it blinds everything about the other guy. And it's very difficult to say anything more than that unless you. I will show you. Wait for.
So is it consistent with this not being edge on?
Yes, it is. It is. Yes.
So maybe that is why
There's no evidence for it. That's the point. So in EHT images down the line, we should be able to a possibility of inferring it, provided it also emits in those wavelengths. So there's there are lots of ifs on there. So yeah.
what are the theoretical masses of this?
I'll tell you. I'm just giving you a cartoon. But since you asked, one is actually a billion, so more than a billion. The other one is 100 million of solar mass. So they're crazy scales. So that's the point. Not everybody is a big fan of it, by the way. Yes.
Why not pick something not directly?
There are no observational evidence. That's the point.
So you might get signal when
Yes. So the hope is that such systems are out there. In the next something called the LSST will scan the skies, because the time scale of these things are years. So when you have many such possibility, there are around a dozen supermassive binary black hole candidates, and I consider this also one of them. There's nothing unique here other than big observatories are spending time. That's all. So
If I copy correctly, it's actually an electromagnetic signal.
these are all electromagnetic. So there is no gravitational waves from it for the time being. Yeah. So all these flashes of light are electromagnetic in nature. Yeah. So what am I talking about? So this is the yes. Yeah.
When this black hole goes from one point to the other,
Yes.
in the scale of
Yes.
so how can you be sure that one flash that gets said
How can I?
how can you be sure, for example, one flash that comes in 5 years is due to this data?
Precisely. That's always a problem. So the game is to now predict within, say, days of accuracy that I expect this from that guy, and then observe.
What is the spread of these flashes like let's see rises, what is this?
It's around 2 magnitude difference. So they are not, and there are reasons why I think this is happening. I'll give you the details. Okay. Okay. So we had some publicity stunt on this, and that's what So we actually predicted this and then observed this. That's the game, as I told you. So what are we talking about? This is the reason we are able to make all that prediction. This is an object in our ecliptic. So if you have a small 50-centimeter telescope, you can actually see this guy. Okay, this is V magnitude as a function of time. You can see that there were points from 1890 onwards. Of course, these are photographic plates. So this was actually compiled by one of Maury's students. So what we see is that you essentially eyeball this. So you can see that there are these peaks, which kind of the magnitude goes down, goes up, and all that. And then you look at these flares in recent past, they last usually for a year and year plus. And on that, and they come, these big flashes appear once in 12 years, roughly. Okay. And when you kind of zoom on that, this is the scale of 100 years plus. When you zoom on that, you actually find additional flares like this. You can see there's a background, it's on that. So these are all we have observational. So what we did was we actually predicted in 2009 that there will be a flare like that in 2015. And back in 2018, we did another prediction that there will be another one on 31st July 2019. And then try to observe this and make fool of ourselves. Why? So blazar gives out flares if you are an observer. Predicting those are really stupid thing to do because you make a mockery of yourself. And it's not the first time this has been done. So, but we are theoreticians, we can rush in wherever, angels even say to thread. Okay, so what is this object? It's a 14 magnitude guy. So you can see that that's the Gemini, the twins. So it's in the ecliptic. So that's the guy. It's just a speck of light. And our ancient astronomers were looking at this part of the sky for comets. They were not interested in OJ287 and pulsar timing array. They were just looking for comets and noted that object out there. It turned out to be a variable star in the sense that with respect to this guy or this guy, there are the small guys here too. Its brightness changes. It was supposed to be 14 magnitude. One fine morning or few nights, they will find that this is 12. So they call this as a variable star. And so it's that's what I said. But these days, we know that this is not in our ecliptic. I mean, it's in our ecliptic, but it has nothing to do with the solar system. It's nothing to do even with our galaxy. It's an extra galactic object. It's called an active galactic nuclei. It's just a supermassive black hole, creating mass on a very large rate and kind of creating all sorts of radiation. So the cartoon is that this. So you have a black hole there. It's actually surrounded by the accretion disk. This is the disk I showed that in that movie. The black hole kind of in ours, and it actually creates a jet. And the jet is actually pointing directly to solar system. Hence, it's called a blazar. That's all it is. And EHT and other collaboration, they are not interested in to take photos, okay? That's only for publicity stunt. Their job is to actually explain how these jets are formed observationally, and that's very challenging. And there are models by Blanford and his colleagues, but there's no observational evidence. And EHT will eventually tell you in maybe 10, 15 years time how that is happening. And that's the real mission of EHT. Photo and other things are movie photo and all that. Okay. And more importantly is that it's a synchrotron radiation. Why we say that? Because it's a high polarization. This jet is synchrotron in nature. So it's high polarization. That's very important point. We'll keep that in mind. So you can say that, as I said, it's a jet directly at you. Okay. So as I told you, this is the observational evidence. You find such outbursts once in 12 years. They last for a while, and there are campaigns whenever this happens. And when you zoom on to that, you find such flares. Those flares will go up essentially overnight, and they last for something like a few weeks, not even a month. So that's a signature. And then if you kind of eyeball it, you find a big 60-year period. So this was all kind of put in together in a model proposed. So, and Mori was actually the first one to kind of look at this very carefully. In 96, he actually argued that there are these flares coming from this. This is from 83 and 84. By the time everyone knew that this guy is a blazar, it's nothing to do with our solar system. So people were, so he argued that there's an easy way to explain this by invoking a companion. And that's what essentially he did. So the game is that you have a small black hole, as I showed in that movie, and it's actually it's going around a big black hole. And so the major flares happen when the small black hole approaches the big guy. Why is that? At that time, the accretion disk is tidally perturbed. Once accretion disk is tidally perturbed, it has to be, so you can't have a small star. A small star will not tidally perturb the accretion disk of a primary black hole. So it has to be a massive black hole. It perturbs the accretion disk. And then once you perturb the accretion disk, the flow of matter onto that big black hole will change. And that will give you the big flares. I keep coming back in around 12 years. And then the secondary goes and hits, as you saw in that movie. And that will, but since it's an orbit, right, there will be twice per orbit. So that's what we are saying. However, that's the problem. You cannot just put a binary there, because if it's a binary, it's periodic. It's not periodic. We clearly saw it was going like this, it was going that, and all that. And that comes with because we kind of make it non-periodic or quasi-periodic by bringing in the effect of advanced periastron. And that is and then of course put in a bit of general relativity. So that is precisely what this cartoon, again, I'm going to play this just to get the, sorry. So this is the scenario, and this is actually a post-Newtonian accurate calculation. It's not a cartoon anymore. So that's the black hole with an accretion disk. That's a big guy. This guy is moving around, and you get these flashes of things. And this is not periodic. And that's happening because this is, of course, everyone knows, this is the advance of periastron. This is the same effect which forces the periastron of Mercury, perihelion advance of Mercury, but in a larger framework. Okay. And this also can be used to explain why that 60-year cycle can arise. You can see that the orbit was like this with respect to the plane of the accretion disk, but it changes. So the accretion effects will be lower here because the tidal effects will be lower here because very close to the, whereas this will be maximum here. So that actually can kind of modulate this big flares magnitude. So the cartoon, of course, we don't care. And
orbital plane.
yes, so this is the plane of the guy, and it has an inclination with respect to the accretion disk, and that changes. And so many things can be explained. The details are, of course, different. So okay, so that's what the model is. Again, I'm going to put it out here. So you need numbers. The numbers are there. It's around 20 billion solar mass. It's not the largest one. This is around 100 million. It's on a highly eccentric 12-year orbit, eccentricity around 0.6. You can see that this is essentially 20,000 AU. It's around 1/5 of a light year. It's very compact. And how do you compute these things? As I told you, these were available from the photographic plate. So in 96, Maury and his students kind of looked at the photographic plates and argued that I can obtain 5 flares from the data. I mean, they were doing a decent job. 5 flares mean I have 4 intervals of time. So I fit 4 parameters. Not very different from what we are trying to do. Whether something can be fitted, we can theoretically, the details are different.
But the calculations are something like you take Schwarzschild solution and then put the mass for it.
No, we actually put Poisson-Newtonian. It's Schwarzschild, but the companion mass, we actually bring in as a mass ratio. It's not a test particle. And there are reasons for that. I will go into the detail. So you cannot use test particle approximation here. The mass ratio is of the order of 100. That's not really test particle. The galactic center stars are test particle because the ratio is 10⁻⁶ or -6, whichever way you want to look at it. It's not. So hence Poisson-Newtonian. So you can actually do this.
What's the distance scale between these two?
So that's I said. This entire system is around 20,000 AU, or 1/5 of a light year, roughly. So it's very compact. Hence, it's emitting gravitational wave. If this was 10 times more, it will not emit gravitational wave and merge in the time of the, So that's another thing. So as I told you, the galaxies come and the black hole inside them will have to merge. And that's where the problem is. Okay.
How far is this system?
How far?
Is this system?
Where this guy is in this. It's a redshift around 0.3. So it's an active galactic nuclei. It's so far away. It's not in our neighborhood. It's not in our galaxy. It is not even, it's quite far away for optically visible. And that's why Martin Schmidt became so famous, right? He was also looking at some stellar spectrum and said that, hey, the lines are moving all over the place. So all lines were shifted by a redshift of, something like 0.1 or something at that time, back in 60 years ago. So it's exactly, here is a bit more complicated because there are no lines. It's a very flat spectrum. He was looking at other configuration of the same system. But fortunately, as I said, the jet was not pointing towards us and the quasars, that's what it said. So the black holes and general relativists would not have been functional these days if these active galactic nuclei were not discovered. Because they required, you have an object which can be seen at gigaparsec distances, looks like a star. The only explanation is black hole. Nothing can beat it. And then once you say black holes are real, then relativists are in fact, and that's what we are all. Yeah. Okay. Yes. Yes. We are just seeing the jet. So I showed the cartoon here of this guy. Let me go back to this. Yeah, I think just missed this here. So this is, the cartoon says that all active galactic nuclei are various manifestation of this. Here is the guy, we are just looking at the, and that's why it's actually a highly, polarization is very high. Good question. It's there, but there are no features. So, usually they don't even look at it in lower frequencies. They go higher because they want to track, some resolve that beam at the higher frequencies. Polarization in optical to various are there, obviously. I haven't seen papers, but this has been followed by the people in just the, flux density has been done up to 8 gigahertz onwards by what was this observatory near I can measure, show whatever it's got, and all those guys are monitoring it. From there's a BU Boston group has this archival. Okay. Yes.
This player events.
Yeah.
This, this,
Mhm.
not yet affected.
Okay. So are you asking the question because the black hole is passing through the gravitation, the disk, whether the trajectory gets affected? Thank you. I know, of course, we computed that. That's what the theoretician do. In Loki's paper, we actually argue that it's sort of a 5 pn effect. It's a very tiny effect, so can be ignored. So there is a discussion on that. I don't have the slide, but I can open up the paper for you. Yeah. Okay. So, but this is not good enough. I mean, you can make this statement and go away. People will not trust you. So what we are saying is that, well, there is astrophysical inputs. These flares, the typical flares are not like that. This guy actually very rapidly rise over a night or a day. It's up to you. And so the game is that this black hole is moving with velocities which are like 0.01. So it's a accretion disk. It creates a spherical curve of a hot bubble for all practical purposes. And then, because this bubble has given so much kinetic energy that the photons cannot escape. So it's dark. But it expands. And that expansion will bring down the temperature. And at that point, when the photons can escape from that kind of a plasma, you will see the entire radiation coming out in a very short time. And that we know is called arresting radiation. That's the thermal Bromstead law. You can sort of estimate, and there was some numerical simulations showing that this is roughly 300 to 500,000 Kelvin. And that is an important part because thermal Bromstead are not polarized. So you will monitor the guy. If you have sufficient polarization data, you should find polarization going down from OJ287. Without that, editors will not agree that this is what you are talking about. Anything can happen, as you correctly pointed out. Okay, so that's what to say. So essentially, this is another one. Thermal Bromstead component is predicted in the theory. It brings down the polarization. We look for that too. But unfortunately, for ancient observation, there is no such possibility. The polarization started very recently. But as I told you, the hit happens and the spherical sphere develops and cools and all that. So there is a delay. As a theoretician, we have a dimensionless time delay on that. So that's a fitting parameter. And all this was possible by 2005, 2006, Mori was able to get this 6 well-timed outburst. So this was the picture at that time. So then you can actually have a possible solution. Once you have a possible solution, you have to make predictions. There's nothing more there. So you have to go and make a prediction. Otherwise, you make a fool of yourself. So Mori did that. So next outburst, you can see that this came somewhere in 2006. And the prediction was that it would happen on something like September 13, 2007. I was not part of this effort. I was doing happily post-Newtonian calculations. And this is, it's actually in Milijansky. This is unpolarized component because there were a campaign. So you can see that that guy goes up like that and comes down like this. This is all you have. You can see the fits are pretty bad. You can see all sorts of points here. But this was good enough to argue at that time. Well, it looks like a black hole binary. And then this came in a Nature paper. And the important thing was he was taking some equations from a textbook and integrating it. And he wrote an argument said that if I have not kept so-called gravitational emission contribution, this prediction will be delayed by 20 days. Okay, so the paper came, it came. So, and I was lecturing in Turku on a post-Newtonian for n-body people. So Mori came and gave me this paper. I said, I don't read Nature paper. I don't know how to even read those. I read only GRQ, classical and quantum gravity or post-Newtonian physical review. That's all I know. Maybe some GRG papers, classic. So he explained to me, this is how you do that. The only difference is this guy. Oh, I said, oh, I never heard about that. So this was the picture at that time. And then the question arises, that's done, what next? So one of the students went into Harvard, and there are this archive of photographic plates. So they're properly done. Some of them actually taken from the Thuringia Observatory. So they came up with this table saying that the possibility there is an outburst in 57, definitely, but there may be 1906 and 1912. In fact, they were looking for the outburst just in the 40s. There were a couple of them, but there were no observation. This is war, there's no observation. But it turned out that maybe Osmania University might have been looking at it, because we were not really, and that was one of the best observatory at that time. They were scanning skies, but unfortunately those observations are not available. So he argued that I have 9 observe outburst, and what can you do? So that's where the post-Newtonian came. I said, well, don't you put the spin? So he was using Schwarzschild kind of post-Newtonian non-spinning black hole. I said, why don't you put spin? And that's where I came. So I worked on something called post-Newtonian approximation to GR. So this is essentially general relativity, dynamics of black hole binaries. I said corrections to Newtonian as various orders, like 1 over c square, 1 over cq, 1 over c4. And then if there are black hole with spins, the spins also precess, geodetic spins, everyone knows that. There are corrections to that and blah, blah. So I'm familiar with this guy. So we sort of incorporated that and came up with an updated version of the thing. So that's what it is. So in 2020, we said, oh, next outburst should come somewhere in 2015. And important thing is that late 2015 is important, because I told you this guy is in ecliptic. So once in ecliptic, what does that mean? Once in a while, it will go near sun. Once it's near the sun, no optical telescope will look at it, because too bright guy. So nothing will happen. So there will be always gaps in the observation of OJ287. But this was easy to detect. So we wrote a proposal at that time. Was a bad thing to do. We said that this will happen during November to February 2016, because we didn't have a good constraint on the Kerr parameter. And we said, for the observer, this is not time. The small telescopes usually don't work with like in a proposal. So in order to attract the attention of observers, we said, if the outburst happen, so 1st of January 2016, the Kerr parameter will be 0.25, error bars are good. Why don't you guys do this? So that's what happened. And so there was a campaign launched. And this coincides with some other amazing activities in late 2015, but that's a different story. And it came. So it came in December 5th. It actually peaked like that. So this is what is plotted here is, I have a delta observation here. As I told you, there's a star near OJ287. So we do something called differential photometry. We compare always with the star. The star is not changing like our sun. So it's very nice. That's actually in our galaxy too. So we are very safe. So this thing happened, and then this went down. That's not good enough technically, because they will say that maybe it was there, some other year. You're kind of joking about it. But we had a swift monitoring of the guys. So it has an X-ray telescope with even UV component, UV telescope with it. It can move onto objects rapidly. That's what it's called SIFT. And it was taking daily observation. And that time, we also have Indian optical observers getting us the optical polarization data. So we were able to do this calculation. It's called optical excess emission. I showed you this figure here. So this is our theoretical curve, and you can see that some extra lights are there. So that are, what happens is that the light in our model, obviously, this is not reality, I don't know. So the black hole is still powered by the companion, by the supermassive black hole. It is still dominated by the accretion disk. On that, we get this extra information, extra flare. So there will be always the synchrotron radiation, and the synchrotron radiation will give you something in soft X-ray. This is also well known to observers. So that's precisely what we did. So we could compute from optical polarization data what we call as the Bremsstrahlung flare. We subtracted that from the actual observation and tried to find the correlation with this soft X-ray outburst or whatever we saw. And that turned out to be very nice. So the referee was very happy. So the paper came, and turned out that this calculation was not done properly in a statistical sense. I was too annoyed with that kind of accuracy, but that's the way we fit in Maury's model. It's not a Bayesian code in those days. So this happened. So this was the picture at that time. So you can see that this, so this is the trajectory. In 2007, this happened. And then in 2015, we were talking about something here. So this flare, the flare need not be like that. I mean, so sometimes, so this is both times. So this is what we saw. So the black hole came along. So the black hole came from the direction of the observation. And then, so at that time, there was some observation. We were trying to do something called the intraday variability, ask me. That's to see whether the secondary black hole has any emission to the beam, so that we can say something about the secondary, but it turned out to be a disaster observationally. Anyway. Okay, now this is not working. Okay, now it's working. Okay. Okay. Yes.
How long does it last?
Which one? Oh, so that flare in this, are you talking about this? This went on for something like 2 weeks. So it peaked around first week of December, but it followed up for something like just before Christmas, things were going down from this level. So, yeah.
So I was wondering, earlier you don't spin and the prediction match.
Yeah, so there is one spin we can fit.
Why did the previous one match? Now,
Because we didn't have more data points in our model. So every prediction earlier the prediction for 2007 was based on something like 6 data points.
the previous prediction would have been wrong.
In principle, yes, but we didn't have that sensitivity. So we have a model, we try to fit. So it is somewhat similar to the what you call as the comets. We only have few observations, and then we try to get the entire trajectory. So as you come closer and closer, we get better observation, and then we can say whether it will go where and all that. Oumuamua is a classic example of that. So here, because of that kind of fitting, we have a model, try to fit that, and we have additional inputs, which is what I told you about from the photographic plates. We assume these are the things. We have a prediction, but that prediction was uncertain because we didn't have any good constraints on that model. Am I clear what I'm trying to say? We can, yeah. So, so once you fix with an observation, then other ones you have, because these photographic plates, they are not very clear because they don't do every day. So we get something.
It's an empirical fit.
It isn't.
Dynamic.
Oh, it's an empirical fit, clearly. Yeah, it's not.
By all this explanation, it is a dynamic.
No. Provided we can actually follow the light curve. That kind of following light curve didn't quite happen in the past.
So this very strong physics, the dynamic.
Yeah, but that's coming from theory.
And that's what you're fitting.
That's right. That's the.
Leave out the spin. Your prediction should be off.
Yes, if you have monitored all the outputs properly, and then I try to fit, it will not match. But now we have additional. I will kind of give you a flavor for that. Okay. Okay. So what we did was. Okay, so we went to go ahead and then try to improve the post-Newtonian corrections. That's where Logi walked in, and there was a reason for that. That reason is something we discussed today. So in post-Newtonian, you have lots of these terms which are corrections coming from the dynamics. So we have to add terms. So Maury was doing only up to this term. It's called the Newtonian emission of gravitational wave. So if you look at neutron star black hole, this system is unequal mass. In LIGO, if the actual neutron star black hole binary will be something like 3,500 cycles from the dominant called post-Newtonian order. The other guy will give you, the next correction will give you 200 cycles. But you can see that there is a contribution called tail. It's a highly nonlinear scattering of gravitational wave from the space-time curvature itself. It subtracts 180. And this is a problem. So Thibault knew about it, and this was computed. This is where the Christodoulou argument I was talking about. Christodoulou argued that the tail depends on the entire history. Therefore, you cannot make templates. How do you make templates? If it depends on past history of the source, I don't know that. So there were calculations done in a Feynman diagram way. Anyway, so these things were computed. It's a memory. Christodoulou memory paper was a classic 30 years ago. But the memory can be split into two parts. One is the tail contribution. It's a non-hereditary, it's a hereditary contribution. It has a memory as well as tail. That's the way we kind of talk about. This does not follow the retarded time. That's the point here. Anyway, so in fact, this calculation, the prediction we are going to make, we were forced to do similar thing, because when you try to put this term, Maury's solution disappeared. And then we are forced to take this contribution precisely because of this effect. So this is another way of saying we were tracking the trajectory proper with existing solution, because these are all higher order. Spin is actually a lower order. It comes down here a bit, and conservative and other thing. So this was very, I mean, as a theoretician, I was very happy, because quadrupolar, you get a solution. You add this term, boom, solution disappears. Maury's model is wrong. We were forced to, and I gave that argument, we did some theoretical calculation to show that. So so this has two different things. This was templates people use for LIGO, what we kind of adapted that in our prescription. Anyway, so we actually, and then we went back to show that there was some optical data. We went back to the actual light curves and see whether earlier predictions are now consistent with the model. It turned out to be consistent with 17 epochs, consistent. So we have an R value for these things, but it's 7 more than what's actually required in our model. Okay, so then we actually, this was a paper, and authenticating the presence of this guy, and a prediction that the next one will peak on July 31st, 2019. So very clear prediction, and Loki's thesis will come after this. Okay, so that was a problem. We said we are going to do it, but I had and this was actually written by pretty decent guys out there, but I have a short circuit for it. I was confident to write that, even though it was there in the observation. I knew that there would be no observation of OJ287 during July, because it was too close to the sun. It takes a summer break, so nobody will observe it. So that's what I said. Because this is an ecliptic, and OJ287, one can show, anyone can with a telescope can prove me that the Gemini, the twins, cannot be seen during the summer. Northern summer, not the southern. And that's precisely the case. So no optical telescope will look at it. So we can, I mean, worst case scenario, Loki's thesis will go ahead. But something else came up. Maury said, oh, I have a student, former student, he's actually working for Spitzer in Caltech. So there's a Spitzer Space Telescope. It's one of the venerated great observatories of ancient times, 30 years ago, 20 years ago. This became a warm Spitzer because the cooling has gone away. It was drifting away from Earth. In July 2019, this was something like 3 million miles away from Earth, which means it has a vantage point to observe OJ287. But this is an infrared guy. So we wrote a proposal, and I actually was visiting RRI at that time. You can see that only I can write that kind of crap. Predicted Eddington flare. Why Eddington flare? Because 2019 is 100 years of Einstein test. So testing an observational test for black hole no-hair theorem using Spitzer. Spitzer was meant for none of these, okay? So I think the referee came, I mean, it's a proposal, but still somebody, it's kind of funny, I have never seen a proposal like this. Obviously, this is written by the post-Newtonian guy. So we wrote it and we got it accepted. And so this was the prediction, this is how it's said. But when you look at this Loki's paper, we actually argued that 2007 and 2019 flare should look similar. The reason is that the inclination orbit and all that, you can see that it comes here. So there's a flare somewhere in 2015, okay? And then it goes, and there is a flare in 2022, but their trajectories are very different. But here, we argued that it looks like the flare of 2019 should be fairly similar to 2007. It's our prediction. There's no guarantee. We can't make anything. And this is the data. It's the data from Spitzer, and Spitzer actually missed the earlier part. The peak it could not find. That's okay, but it has actually follow up. So this is the theoretical curve from 2007. Kind of, it's a 9th order polynomial moved as predicted by us. And we actually subtract certain thing by that amount, because that light curve was actually an optical wavelength. This is infrared. So there are reasons to move this. And this needs to be verified. We did that because Spitzer could see the same guy in March, and we didn't expect base to change substantially like this. So we had optical and infrared to make that kind of statement, and it came, and that gave the confidence. So yes.
Why Spitzer? Why not Herschel?
None of them can actually do any of this. So we need this. No, they were all near Earth, right? So we tried solar observatories because they can see very close to the sun, right? Spitzer was quite far away from Earth. Okay, now it's actually dismantled. This was the last big result from Spitzer. That's what we claim. After that, they dismantled the thing by early 20. Before the COVID came.
Near the sun, right?
Correct. From the Earth point of view, but when it moved this to 3 million kilometers away from Earth, you can still, that extended angle was good enough for Spitzer to see. And this was warm Spitzer. They might not have done this if it was actually properly functioning, because the coolants are all gone. So they said, fine, why not?
Sorry, how much some X-ray?
No. So because these guys are all X-ray sources, right? There are flares from sun and all that. So no. So anyway, so this is the publicity. Hey, watch this movie because I'm trying to get 1 million views. So, okay. So we are now thinking that we will turn this into actually test for general relativity. This plot is the potential. So it's essentially V over C square as a function of the mass. It's a log-log plot. So you can see that this is where on ground we test general relativity. This is where we actually have precision of Mercury. So you can see that it's very weak gravitational field 10⁻⁻⁸, V square by C square. This is Hull-Taylor. We can see that now it's getting into 10⁻⁶. This is obviously the star, the galactic center, because the mass is 10⁻⁶ kind of thing. But now the interesting thing is that LIGO is essentially seeing the last Eobus, but we still have a good place for OJ287 out there. So if we can do that eventually, hopefully, it will be interesting. But this is now, there are too many people doing too many things. So it's kind of, so for example, the classic thing is to actually look for Yukawa kind of a variation. We can have important implication. Anyway, so, so I'm not going to talk about it. It actually happened in our model. This was this summer, 2022, yes. This was again, there was no observation. We suspect there's a paper coming out. There's actually a paper put out. It's all sorts of crap going on there. So we think it happened as predicted in Loki's paper, which was well in the summer, because we have the pre-flare and after thing. That's sort of consistent, but that's all we can say. But the next one will be when he definitely will have a faculty position, so he can follow it up. So. Okay, why this is, okay, so that's all nice, but yeah. So it's coming again, the prediction was in 2018, okay? We didn't change anything, but we thought maybe we can track the earlier part of the, flare if possible, and after it's consistent. There's a paper being written right now. Okay, so we thought, what about Event Horizon? Because they are interested in this guy. It's OJ287 is actually routinely one of the nice calibrator for such high frequency observation, and it can resolve up to 50 micro-arc second level. So why not? And so you can actually compute if what kind of shadow it will create. No. So the radio is actually at least up to kind of 3 gigahertz and above, are coming way ahead in the jet. And it doesn't carry that information. We are yet to find a correlation from the radio light curve and the impact in optical light curve. So there was, actually you guys, you were doing that, right? No, so far we haven't come up with anything. Yeah, so that becomes higher. That's what they're talking about.
That would be independent of this problem. But how do you know every variant comes at the same place?
Yeah, no, not really. No. Now next one is actually in not in summer. So don't worry.
But if it is radio,
Yeah, 32. Yeah, it's pretty good. No, precisely. You need independent observation. Otherwise, this is not going to work. And that's precisely we are after EHT, guys. Or they're after us, I will say. So this is the prediction from Loki's paper. This is the direction of the secondary jet. So if you come to that kind of resolution, you should be able to identify, provided the secondary has a jet, and in our model actually should point somewhere else. So it's a prediction, not verified.
how do you get the secondary gas prediction, the direction prediction?
Well, we associate it with the direction of the spin. So essentially that, it doesn't matter. Okay, but we are not so, but you can see that we are actually part of this game called the Global Millimeter Wave Array. India is not part of it. It's radio. But so, no, let me finish. I'm not gone there. So this is, you can see that there are papers written like this, and you will find some Gopakumar and Lankeshwar Day and Maury Walton. We have nothing to do with this. We have been drafted to make those lines here. Our high fidelity images are consistent with the supermassive black hole. That's the statement we have to kind of interpret for them. So we are drafted in as in TIFR. I'm not part of it. I'm only doing it as a personal. Okay. So, and in fact, this is something Balchandra was involved in it. I mean, he's not part of this effort, but Radio Astron. So this was the Russian telescope which went all the way to moon to. You used to go for all these meetings and all that.
That was something else.
Okay. Okay. No, OJ287, I know. So again, they were asked us to kind of clarify from our model. Why are we doing all that? Because there was a picture, as I said, we want to move away from optical. We know that in binary black hole, and we associate the radio jet, we can track the direction of the radio jet. What will happen? So this is the scenario, theoretical. So this is the line of sight, straight. So the jet is inclined with some angle. It gets projected onto the plane of the sky. If you look up, this is the sky plane. So you can see this blob. You can actually measure that orientation of that. It's called it's called position angle. This position angle in binary black hole will change in a certain way. So the game is that now we will ask, we don't have the telescopes, we don't even have how to analyze. So, but we predicted that with some earlier, you can say very high uncertain values. We actually have a prediction for various frequencies. This is 86, this is 43, and this is, if I'm not mistaken, 15 or something like that. Okay, so these are the predictions. You can see there was a prediction like that, and people are now after it. So this is these are the observation. This observation happens, but the data comes after 3 years. Papers. So let me. So this is the Loki's model. The model was created with this green points, and there were campaigns in 2017 with ALMA observing OJ287. You can see 3.5 millimeter, and then there was in 18 no ALMA. We didn't get time. Yeah, it's radio. It's all radio. It's a millimeter telescope, 86 gigahertz. They just look at the jet. They can actually image this. Then they can say how the position angle with respect to certain frame they have. And this is 2019 without ALMA. So this ALMA, no time on 2019, then the COVID came. So you can see we have a prediction. So there are 3 of them matching. Papers will come out. I'm not going to say. So last week we've submitted another proposal just before I came. So this is again for the 2024. Okay, 23. So this is actually data analyzed on 21. So this observation happens somewhere around March end. So you have to get the time well in advance. ALMA is a very expensive instrument. It costs $2 billion to build. So naturally, they're not going to give you left and right. So we have my collaboration. So this proposal, now the proposal has additional point. Again, not public for the time. I'm just showing it. I will be short if I show this in a conference. So this is showing off 2017, 2018, and 2021. Things look good, not yet, because we want more time. So I will say still not functioning. I won't go all the way up. So that's the game going on. Papers will come out at some point of time, but that's not good enough, right? I will not, even if it follows that, I will not guess a supermassive black hole. I am the most vocal critic of this, because we want more data, more data, more data. That's the point. But the classic thing will happen, we get gravitational wave out of it. Then nobody can object to that. And that's the game that will happen, because this is the game, as I told you. This is our scenario. We will use binary pulsars to look for gravitational wave signature from OJ287. So you need to model expected signals, and that's being done. As I told you this, so we are part of IPTA. I don't have to tell this crowd. Balchandra led that effort and even brought the IPTA meeting to Pune. And so this is in PTA, this t-shirt is thanks to Balchandra. This effort all, puzzle, of course, puzzle, but without Balchandra, there is no t-shirt. That's what I will argue. Okay, doesn't matter. So Pratik and all that. I mean, this is amazing. I don't do anything here other than a publicity stunt. So there's amazing data we are actually getting part of, but we also compute the expected PTA signals from such system. This is a very nice paper by Loki, and it's followed up with another one. This is from Abhimanyu. You can see that we actually can compute this quadrupolar structure now. And so the codes are actually incorporated into IPTA framework. And so we are actually putting spin and other thing. This paper has been delayed for things which I am goofing up. So that hopefully will happen soon. And why are we interested in all this? Look at that. SKA era PTA. This is not from a PTA paper. It's actually coming from Fermi-Lat. They say that once you get the strength of the gravitational wave into 10 raised to minus 14 kind of thing, you can see that things start happening. You can even go up to cosmic string if there exists. So string theory can be verified. You will find isolated gravitational wave from inflation if you are interested. Supermassive black holes will come up. But you can see that SKA will be required. It's a science paper. It's not written by us. It's by Fermi-Lat team. But SKA is already here. Oh, today's notes, I have to edit that. I gave a colloquium somewhere in early December. And that's today, December 5th, I gave the colloquium. At that time, Jonathan actually put out this, SKA is already under construction. It will happen. And once that happens, we will open up all sorts of crap in the sense of we can actually do, it's a persistent gravitational wave source. If you can extract it, you have already optical observation. There are great observatories, X-ray, 30-meter telescope can actually be fantastic to look at OJ287 for spectral lines and how they move. In fact, my Korean colleagues already wanted to do astrometry by 3 frequencies together in something called FPT. I was talking to you about that. So there will be lots of effort on this guy. That's Loki and Mori kind of ensure that. So, but it's not there. It's not just that. Such AGNs will also give you neutrinos. So we are not talking about just some electromagnetic waves, some gamma rays. No, even neutrinos can come from the guy. This is going to be very interesting. It may happen maybe in 10, 15 years, but it will hopefully happen. And hence we think hopefully this message can, this can be further refined. And we will have actual monitoring of this guy with NGEHD, gravitational waveforms, one-to-one correspondence that can just open up. Maybe at that time, KM3 net or something will actually see neutrinos from it. So this can open up interesting avenues, and that's what we are trying to do. And of course, this is all possible thanks to all my younger colleagues in both in what we call as a team eccentric. There are plenty of them here. Prerna sitting here, Shubhajit, other guys have gone to America, and you have lots of them. Fasal is there, of course. Avinash actually worked on the radio data and all that. Nothing happened because I got busy with other things. So hopefully something will come out of all that. And with that, we have the multi-messenger and persistent at cosmological distances. Hopefully, Loki and Abhimanyu and Avinash and Shubhajit and Prerna can all talk about it in the coming years here. That's what I hope will happen. Thank you very much, and I will be happy to take questions.
Thank you for such an exciting talk. Questions?
Yes.
It's ready.
Oh yeah. If you believe in this model, merger will happen in 10,000 years, roughly. And that's what
We will not be there.
that's why people hate it, because it's too crazy system. Imagine there are so many binary black holes merger happening in our universe, but capturing something, for example, binary pulsar was required to fund LIGO. Nobody will fund LIGO if you have no binary pulsar, because binary pulsar show that gravitational wave exists, and it actually takes away energy and angular momentum, at least energy, because they could not get the E dot under control. So, and that is required to build an instrument which is essentially $500 million. And that happened just after Nobel Prize was awarded, LIGO.
So the merger is already occurred. We
No.
We will see it after 10.
Of course. No, of course. No, but the LIGO guys were supposed to merge in something like 50 million years later. But 50 million years is nothing. And that's what we are seeing now. Binary pulsar was within our galaxy. And then Balchandra was involved in the discovery of double pulsar, which was going to merge, which will merge in something like 40 million to 50. I can't remember exact number. So those are confirmed. All now you do is in astronomy, we first establish where something happening here, then you go look for wider places, and so then your ability to. So the hope is that LSST will see many such things which will give more confidence to PTAs. And then that's the game going to play out in the next 5 to 6 years. Yeah. Yes, Prabhu.
So that is the volume is more such objects and what kind of a measure sector per year, per 10 year.
40 megaparsec is only for the neutron star binaries. The LIGOs are 40 megaparsec. 0.3.
So in such systems, what is the
So this is definitely a strong candidate. I mean, unequal mass and all that. So it may be semi-merger galaxy can give you this. There is not many. The reason is that, as Shantanu will say, when you have illustrious and all that simulation, they will give you a resolution not at kiloparsec. It's almost megaparsec. If the boxes are megaparsec or something, right? So then you bring, so they can show that the galaxies can come closer, which means they will merge after some 100 million or something years. But the black hole merger is a big problem. The galaxies can go through. For example, Andromeda will, splash onto our galaxy. But then our galaxy monster will merge with Andromeda. That's a very uncertain question because there are lots of uncertainties there, and that cannot be, hence the rate is a problem.
redshift process is
Correct. So what will happen is that instead of the chirp mass I was talking about, because it can be a redshifted one. So this also, LIGO doesn't care because we have 40 megaparsec, there's no redshift. So eventually for LISA, there is a degeneracy between the redshift and the chirp mass. So, and that cannot be broken unless you find other things. Yeah. So it's there in gravitational wave too. So just like so the reason is that we are looking for an amplitude. Yes. So the chirp mass can be lower. It can be higher with a lower distance. So there's a chirp mass is in the numerator and the luminosity distance at the denominator. So we get a combination. When you include cosmological consideration, it can be a massive galaxy further away or less galaxy nearby. So that uncertainty will be there. Therefore, electromagnetic counterparts can break that because they will immediately give you a spectrum. I will fix immediately the luminosity distance and then I immediately get the chirp mass. But this is only for LISA. LIGO or third generation, of course, will be problem. Yeah. Am I clear?
Yeah, PTA also.
Yeah, PTA will also, but the hope is that most of the PTA sources are going to be with AGNs. So by default, we will see something. Hence, yeah. So the incompleteness of the galactic survey may not be a problem for us in the sense that we suspect, for example, if there is a suspicion that the background is perturbed by something, and that can be a isolated gravitational wave, we roughly figure out because the pulsars around it are more sensitive. So you already get some sort of a direction, and we roughly know the amplitude. So we should be able to look for possible AGNs from that direction. Whereas in LIGO, it's a transient. You get usually 40 square degrees and all that. Then it's a problem. Usually 100 square degrees, but yeah.
Are there any other components via such plate?
No, not really. But now they are slowly bringing it into LIGO. So there was a LIGO event, and Matthew Graham actually argued that it looks like a black hole is actually formed in accretion disk and kicked out. Hence, it gives you a flare, which CTF saw and all that. But those are, but there are plenty of black hole candidates, binary candidates. We have something called TikTok. Avinash is working on that, and there is another called 2131, I guess. So it's actually radio observation, again high frequency 21.
Just to ask, we've seen flares, EV gamma ray flares from other data, PTA 2155.
Yeah, but
Markarian 421.
correct. So there are Markarian is also 421 is actually 401 is considered as a binary. 401 is considered as a binary black hole.
Or EV gamma ray flare.
Yeah, but that's not sufficient. You need repeat to get a binary, right?
Yeah.
That's difficult.
So no periodic deviation in your class.
Oh yeah, there are plenty of those guys, but then they will
PKS or is it
not PKS, no, PG 13 or 4 or something. Yeah. So it has not really every time, but then people will say that's red noise. So that's another problem. In fact, Avinash actually adapted the code and all that based on that. So if you find periodic, Roger's argument for US source is that it's not periodic, it's sinusoid. He argues, he hates this periodic business because when they're against those arguments, so he wants to, no, that's not periodic, it's sinusoid. Difference is subtle, but yeah. So there are few, but again, there is no confirmation per se. So US source will be looked at by KBN guys. I'm trying to push them because they have, as I told you, multi-frequency observation. So they can take care of all the atmospheric. It is smaller, yeah. That's precisely. It's a couple of years.
They're planning to resolve it out of it.
At least they want to see the astrometry. Resolve maybe.
is especially
It's-
possibly 2.85 in the
Yeah.
it's nearby.
It-
get to this city.
It's not nearby, it's far away.
This point is important.
Then how will you resolve it?
They claim that they
You
can.
can't resolve this.
Yeah, but this is a blazar. The other way is not a blazar.
But black holes are the
No,
same.
that's a blazar too. That's also blazar too.
Everything is a blazar there.
Yeah, it's a blazar. Yeah,
So,
not TikTok.
so if you can't resolve this,
Mhm.
alien cannot resolve.
Well, he claims that he's
You're saying it's even further than this.
it's not the solution, it's the astrometry. So they can latch on to some of these emission regions, which they can resolve, and that moves. The claim is that they can
So
see
you
that,
have to resolve to the scale on which the binary is.
yes,
If you cannot do that for OJ,
right.
you can't do it for anything which is further out of it.
I know, but they will do both. They're going to attempt. So here the claim,
And in this GMBA and other
Right.
campaigns,
Yeah.
you also had the space interface program
Sure.
there.
Yeah.
It gave you UV coverage.
correct.
But the extra coverage is there.
And
With a ground-based VHA, it is impossible.
so KVN plan is that they have this 3 frequencies like GMRT, simultaneous observation.
See, resolution
Not just KVN. They wanted to do this for the GMVA. So they are arguing for that. That's the conference they had in
yeah, so
Bonn.
what's the baseline,
Then it should be baseline of GMVA,
which is the Earth.
Earth.
Here it is beyond Earth. It is moon.
No. I only showed, that was only 21 gigahertz. This one, all the
The radio astron one,
radio astronaut was low frequency.
almost up to the moon.
Yeah, but low frequency. It was 21 gigahertz.
But
This one is,
but the ordinary
128.
magnitude of the baseline is so large
Correct.
that you get a very good resolution there.
Yeah, I agree.
There also, as you are saying, it did not resolve the thing. Right?
Yeah. So anything you are talking, yeah, I mean, so this is one you're talking about. So their resolution was up to 50 micro arc second. That's what.
So,
Only one epoch. The argument,
how high you are going? You are going by a factor of 4.
yes,
Okay, but your baseline is reducing by several orders
of magnitude.
So your resolution cannot be better.
No, but this was only one epoch.
Because it doesn't matter.
Yeah.
Resolution is
No, what I'm saying is so, okay, this is what these guys are very happy about incorporating Loki into this. So we want to see this kind of orbital separation.
And see other things.
Yeah.
I agree. Where you don't need resolution, you can see those things. Some variation, light curve variation, for example, you don't care. Whether
Yeah,
it's
nobody cares. Yeah,
the resolution.
Right.
Variability you can detect,
right.
but if you can't resolve this,
Ah.
then PKs you can't hope to resolve it.
Yeah, but I think there's the claim is that they will try.
So that claim is wrong.
Okay, okay. I will tell Taekwan. So
Unless I'm missing something.
I should ask him too. He said, give me all the list. We will try something. Because many of the sources are not strong in 128 gigahertz, right? 3.5 million.
They're all derivative sources.
Yeah, so they also need that. Of course, further away it becomes. But OJ287 is a classic, they will do that.
But my argument is not on the intensity, it is simply on the resolution.
The resolution,
of the processor.
yes,
It
right, okay.
depends on the baseline and baseline only,
Correct.
nothing else.
So as you correctly pointed out, they are in Amsterdam. Some of the guys are actually want a millimeter, kind of 128 gigahertz in space, precisely for this kind
So
of
that
thing.
is the millimetron.
Exactly,
And
or some version of it.
if it is launched by Russians maybe in the next decade, then yes, you can hope.
Many of this can be done. That's the aim, but it will not go.
Millimetron will go all the way up to the moon. And
I don't know. The one they are talking about is not going to do that to begin with, and so they are upgrading this. That's what I've been told. There are many proposals. So, but one of the thing again, they were asking us, can you plot something for them for their science cases and all that. So the claim is here. Hopefully, it will give us an additional boost.
yes, I think the best thing would be to focus on the variability of some parameter
Yes.
and show that regardless of the resolution, because variability will come.
Yeah, but still, I will argue that astrometry is the correct thing to do along with the.
So I had a related question.
Yes.
We should not go.
No. Ask, please.
Can you have some kind of, not in OJ, but in some other source, is it possible to have gravitational density?
Oh, yeah.
Because there are these two black
Yeah,
holes going
sure,
on.
sure.
If
Yes.
you have the right mass of the black hole,
Yes.
You can lens a background.
Oh, precisely.
star.
Yes. So this will have to take me to Colombia. So our friend, what's his name? Sultan. So Sultan has kids have come up with this precisely this. They have a binary black hole scenario, something very similar, but they argue that they will see a flare, and the flare is lens. And they have a prediction, but it never happens. But at least they have a scenario. Their claim is that this will be very useful in the LSST regime, because some of these flares, they may not see everything, but in the same guy flares, then they will be able to, because the daily monitoring such deep thing. Shri was arguing that no, CTF will do everything, but not yet. So this will be, yeah. So Sultan has precisely that. I get.
Pick up flaring events which are periodic in that.
Yes. So the argument there is that its lens one has a clear shape, and it will not change polarization and other things. So, and the spectrals, something I can't remember exactly what was they talking about. So that is required.
And it will give you the masses also.
Yeah. Yeah, provided you figure out few of them. So you need a marker of the orbit. That's what it's all about. Yeah, that's what precisely was doing. So, yeah.
Any other questions? Okay. So if no more questions, let us thank.
Thank you very much.
Actually, it was before the talk.